In mathematics, the complex conjugate of a complex number is the number with equal real part and imaginary part equal in magnitude but opposite in sign. For example, the complex conjugate of 3 plus 4i is 3 minus 4i. In polar form, the conjugate of is. This can be shown using Euler's formula. Complex conjugates are important for finding roots of polynomials. According to the complex conjugate root theorem, if a complex number is a root to a polynomial in one variable with real coefficients, so is its conjugate. Notation. The complex conjugate of a complex number is written as OR. The first notation avoids confusion with the notation for the conjugate transpose of a matrix, which can be thought of as a generalization of the complex conjugate. The second is preferred in physics, where dagger is used for the conjugate transpose, while the bar notation is more common in pure mathematics. If a complex number is represented as a 2 times 2 matrix, the notations are identical. In some texts, the complex conjugate of a previous known number is abbreviated as C. For example, writing means properties. The following properties apply for all complex numbers z and w, unless stated otherwise, and can be proven by writing z and w in the form a plus ib. A significant property of the complex conjugate is that a complex number is equal to its complex conjugate if its imaginary part is 0, that is, if the complex number is real. For any two complex numbers w, z, the penultimate relation is involution, i.e., the conjugate of a complex number z is z. The ultimate relation is the method of choice to compute the inverse of a complex number if it is given in rectangular coordinates. If z is non-zero, if is a polynomial with real coefficients, and, then as well. Thus, non-real roots of real polynomials occur in complex conjugate pairs. In general, if is a holomorphic function whose restriction to the real numbers is real-valued, and is defined, then the map from to is a homeomorphism and antilinear, if one considers as a complex vector space over itself. Even though it appears to be a well-behaved function, it is not holomorphic. It reverses orientation, whereas holomorphic functions locally preserve orientation. It is bijective and compatible with the arithmetical operations, and hence is a field automorphism. As it keeps the real numbers fixed, it is an element of the Galois group of the field extension. This Galois group has only two elements, and the identity on. Thus the only two field automorphisms of that leave the real numbers fixed are the identity map and complex conjugation. Use as a variable. Once a complex number OR is given, its conjugate is sufficient to reproduce the parts of the z variable: real part, imaginary part, modulus, argument. Thus the pair of variables and also serve up the plane is to x, y and n. Furthermore, the variable is useful in specifying lines in the plane. Is a line through the origin and perpendicular to, since the real part of is 0 only when the cosine of the angle between n is 0. Similarly, for a fixed complex unit u equals exp, the equation determines the line through in the direction of u. These uses of the conjugate of z as a variable are illustrated in Frank Morley's book Inversive Geometry, written with his son Frank Vigor Morley. Generalizations. The other planar real algebras, dual numbers, and split complex numbers are also explicated by use of complex conjugation. For matrices of complex numbers, where represents the element-by-element conjugation of, contrast this to the property, where represents the conjugate transpose of. Taking the conjugate transpose of complex matrices generalizes complex conjugation. Even more general is the concept of a joint operator for operators on complex Hilbert spaces. All this is subsumed by the asterisk operations of C** algebras. One may also define a conjugation for quaternions and coquaternions. The conjugate of is. Note that all these generalizations are multiplicative only if the factors are reversed. Since the multiplication of planar real algebras is commutative, this reversal is not needed there. There is also an abstract notion of conjugation for vector spaces over the complex numbers. In this context, any antilinear map that satisfies where n is the identity map on for all and for all is called a complex conjugation, or a real structure. As the involution is antilinear, it cannot be the identity map on, of course, is a linear transformation of. If one notes that every complex space V has a real form obtained by taking the same vectors as in the original space and restricting the scalars to be real, the above properties actually define a real structure on the complex vector space. One example of this notion is the conjugate transpose operation of complex matrices defined above. It should be remarked that on generic complex vector spaces there is no canonical notion of complex conjugation.